This is a Thorium Energy Alliance Technology talk from the inaugural Future of Energy Conference, October 2009. To find out more about thorium energy, please visit thoriumenergyalliance.com. This talk is from Paul Houle. It is about computer modeling and simulations of reactors.
A simpler answer is to go to a two-fluid system where inside your reactor you've got some fuel salt and you've got a blanket salt and you've also got a blanket reservoir out here. And because the flux is less in the blanket reservoir, you can improve your breeding ratio. You've also got the advantage of simpler fuel processing because out in the blanket, in a fuel salt, we've got fission products. You've got no thorium. You don't have to deal with that. And in the blanket reservoir, you've got much simpler chemistry too. You've got just thorium and protactinium and U-233. And this also lets you optimize your system parameters. You can put each material where you want to get it. This has the potential for the most highly performing systems. But I'm bringing these issues up not because we need to pick a particular choice, but whatever choices we're going to choose, you've got to quantify the effects. So we need codes that can simulate how well these things really work. And let's see. So the French group that LeBlanc talked about actually did develop a code for doing this type of coupled analysis that uses MCMP as the neutronics engine. And ORNL also had a code developed in the 70s for doing this kind of work too. And if we look at the French work, they actually consider a couple different reactor designs. And they consider some that have graphite and some that don't. They consider a range of designs where, and even for some of their graphite designs, they're able to evade some of the stability problems that the original ORNL design had. It's a 1.5 fluid reactor, so they're putting some thorium. They're putting thorium in a radial blanket. But the big thing you're noticing here is a trade-off in the fissile inventory for thermal versus fast reactors. And that's an issue I'll touch again in a minute. But in their system, they're looking at a system of fuel processing. It's very simplified compared to ORNL designs. Like ORNL, they bubble helium through the fuel to extract insoluble elements. That lets you get rid of xenon, which is a bad neutron poison. It lets you get rid of noble metals. But rather than doing continuous reprocessing, they pull the salt out, process it in the batch every 6 months, and they put it back in. And their goal is near unity breeding. They don't necessarily want to produce large amounts of fuel for export, but they'd be really happy to have something that you'll load up with some U-233, you just put thorium in it. You take fission products out. And a reactor like that could be a really practical power source. Their fuel processing system they're looking at, the thing I'd really emphasize here is you've got choices. And in characterizing the systems we can build, so you've got choices here where they can decide. They want to put neptunium back into the core. They can put other transuranics back into the core. And really, any element you don't like, if it absorbs neutrons, a pretty good answer is to put it back into the core because neutrons in the core will transmute it into something else. And so looking at the thermal spectrum, this shows you what the inventories in the core look like over time. Neutron absorbers are increased, so they have to add a little more U-233. They have to maintain a higher level to stay critical. U-234, U-236, U-235 are created. But the one really interesting issue is you get after 100 years of operation, the reactor has an inventory of it of maybe 60, 70 kilograms of plutonium. That's compared to tons that we produced in the lifespan of a light water reactor. And that plutonium is mainly plutonium-238, which isn't even conceivably usable for weapons. You get other minor actinides, but really in pretty modest amounts. And another factor that they can get a handle on and quantify is production of tritium, because the lithium in the fuel and blanket salts absorbs a few neutrons, produces tritium, but they find that their equilibrium production is about half that of the CANDU reactor. So you're looking at something that, CANDU's been licensed, the Canadians have been living with that. It's a problem that's, looks acceptable and manageable. But now, once we have tools for looking at an individual reactor, the next question is, how do fleeter reactors work when it comes to resource requirements, where materials come from, where they go? This is an outline of a system called Vision that's been developed in the last couple of years for looking primarily at plutonium cycle type systems, where you're either looking at, you want to compare what happens with the current light water reactors to something that burns the actinides in a fast reactor, but something of that maturity hasn't really been developed for a thorium economy yet. But from the Nuclear Green blog, from Charles Barton's blog, we can pull off the back of the envelope calculation because that's what you do when you're a physicist and you don't have something better. And they look at the S-Prism. Fuel cycle study, where these guys find they can take 400 tons of plutonium from our current light water reactor fleet, stuff we've got sitting around in storage, and that's enough to start 33 gigawatt electric of fast reactors that are near breeders. A reactor that you'd feed at U-238 and we just maintain its stock of Q239. A thermal MSR near breeder needs maybe a tenth the physical inventory of that, and that's a big advantage when we're talking about why does thermal breeding matter? Because we need a much smaller physical inventory. We can trade really expensive materials like U233 and plutonium for graphite. And so the same star charge could fuel maybe 300 gigawatt electric of near breeders. And John McCain was talking about building maybe 50 new LWRs. And that's the type of expansion people are talking about in our industry. And S-Prism could expand the industry by, about that much. Significant, but not really world-changing. If we could actually switch over to MSR near breeders, we've got the potential to vastly expand our nuclear industry and talk about serious fossil fuel replacement. So the sort of elements that could be in this type of model is we mine uranium and we mine thorium. We've got a huge amount of waste from LWRs that we ought to do something with. Get rid of that plutonium so we don't have to bury it. Our existing LWR fleet's going to be operating for decades. We could keep running it on uranium oxide fuels. We could run them on fuels that combine uranium and thorium, either as oxide or the type of core thorium power does, which is metal uranium elements so they can get more power out of them. And then we could feed these in to molten salt reactors of various types. We could imagine one that's specialized at converting plutonium to uranium-233. And then a near breeder could be deployed next that could just operate on our existing stocks, producing a really high level of power. In the long term, we could see a transition to advanced breeder, which is able to have maybe a doubling time, 10, 20, 30 years. That could, over the long time, let us expand the size of our thorium economy pretty much as big as we want it. And it's a really major research step is to start developing a code, developing the methods to model these kind of systems and really quantify and show that we're not just talking about cleaning up the waste from today's power plants, but talking about moving forward and making a big difference in the world.